So today we're looking at Digital Lab number 11, shift registers. So under required parts, we're going to be using the breadboard, our wire strippers, and hookup wire. We're going to be using the 7414 Schmidt inverter, the 7474 dual D flip-flops, the 74112 dual JK flip-flop. Remember, your book uses the obsolete 7476. And the new IC we're going to be using this week is the 74194 Universal Shift Register IC. We're going to need our 470 microfarad capacitor, 4 LEDs, 4 330 ohm resistors. Remember, your book uses 150 ohms, but we want to limit the current a little more. And we need a 2K ohm resistor. So as always, when I introduce you to a new part, this is the 74194, which is the Universal Shift Register IC. I always give you a pinout for it, so you can see we have parallel inputs, and we have our basic Q outputs, clock signal on the input, and different control lines that we need to hook up to it. So for the pinouts for the 7414, the 74, and the 112, you need to reference previous labs where I did give you the pinouts when I first introduced the IC. Now under reference sections, we're going to reference Chapter 11, sections 11-1 through 11-4. When you've completed the lab, you should be able to answer solved problems 11.1 all the way up to 11.28. So in your textbook, Sham's Outlines, Digital Principles, Chapter 11 talks about shift registers, and Section 11-1 starts with a basic introduction, and Figure 11-1 shows you different types of shift registers and gives you a graphic of what's happening inside a shift register. Section 11-2 talks about the serial load shift register, and Figure 11-2 gives you the logic diagram of a 4-bit serial load shift right register that we're going to be building today. So Figure 11-3 shows you a timing diagram for the 4-bit serial load shift right register that we're building today. And timing diagrams are important because they give you an idea of the timing between the different signals that affect your shift register. Section 11-3 talks about the parallel load shift register, and Figure 11-5 gives you the logic diagram of a 4-bit parallel load recirculating shift right register that we're going to be building today. And 11-4 talks about TTL shift registers, and they give you the logic symbol for the 74194 Universal Shift Register IC that we're going to be using today. And Figure 11-9 shows you the mode select function table for the 74194 Universal Shift Register IC that we're going to be trying out in our truth table. So Lab Schematic Part A, it's going to be a serial load shift register. And you can see we have 1, 2, 3, 4 D flip-flops, and they're labeled U1A, U1B, so that is on one IC. And then we have U2A and U2B, that is on the second IC. We have a U3 here, and the U3 says it's 1 Hertz. So under Procedure Part A, it says use the circuit of Lab 9B to generate the 1 Hertz input signal. We're to fill in the pin numbers above, construct and test the circuit. The completed truth table to the right uses 1s or 0s. So you notice the clock signal comes in and goes to the first clock, the second clock, the third clock, and the fourth clock. So these are all going to do their thing at the same time. Now these are D-type flip-flops, so when the clock signal comes in, whatever is on the input of the D is going to show up on the Q. So we have a clear line or a reset line that's going to all the little clear inputs, and because they have a bubble going to them, that means they're active low. So when your switch closes or goes to 0, each of these D flip-flops is going to have a 0 on its output. So that should be the first thing you do with your shift register, is actually clear everything. Then we have our D input. So when the switch is down, we're going to put a 0 on the D, and a 0 is going to come out on the output when it gets the clock signal. So if you open the switch, you'll put a logic 1 in. When you get a clock signal, the 1 will come out over here, and then you can close your switch back to 0. So looking at your truth table, the first thing you're going to do is put a 0 on the clear line. It won't matter what's on the data line. Doesn't matter about the clock. All the outputs are going to be 0. And you notice I gave you some hints down the side of the page here. So the hint is we're going to get 0 on our output. Then in the next example, you can see our clear line is high, so it's no longer going to be clearing. We're going to put a 1 on the D input. That's the first D input. We're going to get our clock pulse. So what's going to happen is the 1's going to shift into the A output, which is the Q on the first D flip-flop. The 0 that was there is going to shift into B. The 0 that was there is going to shift into C. And the 0 that was there is going to shift into D. So in this case, you can see the output 0, 0, 0, 1. We're going to continue to keep the clear line high, so it will not be clearing. We're going to change our data to 0. So on the next clock pulse, a 0 will shift into the A, and the 1 will shift into the B. And the 0 will shift into the C, and the 0 shifts into the D. So you can see here, each time we get a clock pulse, that 1 is going to move over 1 position until it goes right off the end of our shift register. So this is a close-up of my circuit. You can see at this end I have the 7414 that's generating my clock pulse. You can see I've used a blue line for the output. I've also used a blue line to bring the clock over to my D flip-flops. So wherever you see a blue line, that is the clock signal. So you can see I've jumpered from one pin to the next pin to get to the next IC. The green lines represent the D input, and they also represent the clear. So I did the clear and the D both in green. The yellow lines are the feedback from one D flip-flop to the next, and they also go out to my outputs. The red line are +5, and the black are grounds. You notice I did not run any of my leads across the ICs, just in case one was defective and I had to change it. So down this end I have my dip switch. I used one switch at either end of the dip package. I've decided to use individual 4.7 k ohm resistors for the pull-ups rather than using one long SIP resistor. The choice is yours. For each switch I use, you need to have a ground line. So on our lab, what they want us to do, in the first row, we're going to activate the clear line. So that's all our outputs at 0. Now in the next step, they want D to be 1, and our clear line is to be 1. And then once the 1 shifts in there, we want to go back to 0 because we just want to see that 1 bit shift across our shift register. There's the 1, and now it goes across our shift register. So filling in my truth table, you can see when the clear line was at 0, all my Q outputs were 0, just like in the hint. And then when my clear line was high, and I put a logic 1 on my data input, my first Q output was 1, and the others were 0. Now I had to move the D switch back to 0 quickly before the next clock pulse came along, and the 1 shifted over 1 position. Then on the next clock pulse, it shifted over another 1 position. Then on the next clock pulse, it shifted over another 1 position. And then after that, all the zeros shifted all the way across. Once you've wired up this first circuit and verified that it is working, demonstrate it to your instructor so they can initial it to indicate that it is complete. So for Lab Schematic Part B, we're going to do a parallel load shift register. You can see that I have to use 5 switches on my dip switch, so now I'm going to use a SIP resistor. And now we've changed the IC to the 112, and we're still going to use the same 1 Hertz signal coming in. Under the procedure for Part B, you can see that we're going to use the circuit of Lab 9B to generate the 1 Hertz signal that we've been doing all along. We have to fill in the pin numbers above, which is very important. We're going to construct and test the circuit, then complete the truth table below using 1s and 0s. Now there is a note here. You only want to load 1, 1 into the shift register. So you get 0, 0, 0, 1. And since you're using a 1 Hertz clock, you must change the A switch quickly before the next clock pulse, or else you will continuously load 1s into your shift register. So that's kind of an important note. As always, I can't stress enough the importance of putting down the pin numbers when you're trying to wire up a circuit. Trying to remember these numbers in your head will confuse you. Now you'll notice down the side of the truth table I've given you a hint of what it should look like. So I want you to notice the dip switch, which we're using to load our numbers, actually goes to the preset line. So when we put a number on here, we're actually activating the presets on here. The presets are active low. So when we put in a 1, it's not presetting. When we put in a 1, it's not presetting. When we put in a 1, it's not presetting. When we put in a 0, it's actually presetting this JK flip-flop to output a logic 1. So I want you to notice over here that the final output of our JK flip-flops, pin 9, the Q, comes back and feeds into the J of the first flip-flop. And the Q0 on pin 7 comes and feeds back to the K of the first flip-flop. So every time this circulates, whatever's on the first flip-flop goes into the second. And then from the second to the third, and then from the third to the fourth, and then from the fourth, it recycles back into the first. So going back to our truth table, you can see the first thing we're going to do is clear our shift register. Then we're going to do a load of a 1 bit into the A position. You'll notice there's no clock signal needed because those presets and clears are asynchronous, meaning they don't wait for the clock signal. And then after that, we're no longer going to be presetting or clearing any of our JK flip-flops. So on the next clock pulse, with that 1 should shift into the B position, and then the C position, and then the D position. And then on the next line, it comes back to the A position, and then over to the B position. So this is my circuit of part C wired up. You can see at this end here I have my 1 Hz signal from the 7414. I have my 74112 and my second 74112, my output LEDs, and my dip switch. Now keep in mind, this first switch here is going to be my clear line. And the 4 switches at this end are going to be for my presets. I've wired up my 4 LEDs, so this is the least significant bit. This is the most significant bit. On my dip switch, I've wired it up so that this is my least significant bit, and this is my most significant bit. So powering on the circuit, you never know what state it's going to start in. So you should start by clearing all your bits. So that's all my bits cleared. Then move your clear bit back up to logic 1. Now our preset lines, you have to move them fairly quickly because we've got a 1 Hz signal coming in, and if you keep the switch down too long, it'll just keep feeding ones straight into our circuit. So if you want to stop your shift register from shifting, the easiest way to do it is to remove the 2K ohm resistor, and you'll notice it stops shifting. Now you can use the clear line to clear, and you can put whatever number you want into your shift register with the preset lines. And then you can put your 2K ohm resistor back into your timer. So to fill in your truth table, move the clear line to the 0 position, clearing all the flip-flops. Move it back to the 1 position. Move the preset line for the least significant bit to 0, and then back to logic 1 quickly. And now you can fill in your truth table. So for your truth table, well, when the clear line was set to logic 0, each of the outputs were at 0. When the preset line for A went to 0, we loaded a 1 into the A output, and zeros were at the other 3 outputs. So then when we moved A's preset line back to logic 1, on the next clock signal, the 1 moved from the A output to the B output, and the A output became 0. On the next clock transition, the output from the B went to the output on the C, and the B's output became 0. Then on the next clock transition, the output from the C became the output on the D, and the C became logic 0. And then on the next clock transition, it circulated through our circuit, and the 1 came out on the A output. And then on the next clock transition, it came out on the B output. So once you've wired up your circuit for part B and verified that it is working, demonstrate it to your instructor so they can initial it to indicate that it is complete. So for the lab schematic, Part C, the TTL Shift Register, you can see we're going to be using all 8 of our switches in our dip switch package. So we're going to use the SIP resistor package for pull-up resistors. Now on my 194, you can see I've put in all the pin numbers. And U3 is a 1 Hertz signal. So under procedure for Part C, it says use the circuit of Lab 9B to generate the 1 Hertz signal. So that's where that comes from. Now looking on here, the first switch of my dip switch is going to be the clear line, followed by S1 and S0, which is the mode of the TTL Shift Register. So I'll show you what that looks like in a second here. We also have pin 2, which is recirculating in from QD. Okay, so that's our data for shifting right. So when we bring something in, we have to bring it in from a couple of data lines. So we've got data for shift right and we got data for shift left. And you can see we have an A, B, C, D input. So these are the preloads, and that's determined by the mode that we select. So we can select preload and it will load in whatever number we put on our dip switch. Our output's going to be QA, followed by QB, followed by QC, followed by QD. Just want to remind everybody that QA is the least significant digit and QD is the most significant digit. In the counter circuits, we had it the other way around, so most significant was over here and least significant was over here. But in this particular circuit, we're going to have least significance starting on this side. So 11-4 in your textbook talks about TTL shift registers, and figure 11-8 gives you the logic symbol for the 74194, and you can see that they've labeled their output so that A comes from QA, followed by B, followed by C, and then lastly by D. We have 2 mode controls, and there's a separate table just to talk about the mode controls. We have the parallel loads, we have the shift right serial input and the shift left serial input. So it's the data for shift right and data for shift left. We have the clock, and you notice the clock symbol does not have a bubble on it, so it goes on the positive transition. And we have a clear line on it that has a bubble on it. So whenever the clear line goes low, all of the 4 outputs go to 0. And then figure 11-9 is the mode select function table for the 74194 Universal Shift Register IC. So I just wanted to give you a close-up of the operating mode table. Notice they use L and H instead of 1s and 0s. So we have the mode where S0 is low and S1 is low. So that's 0, 0. That would be a hold or do nothing. So we'll see no changes on the output when it gets the clock pulse. Now when S0 is low and S1 is high and we get the clock pulse, we will shift left. And when S0 is high and S1 is low, we're going to shift right. And when both S0 and S1 are high, it's going to do the parallel load. So this is our truth table, and I've tried to keep it as close to what was in the textbook as possible. So you can see our parallel load, we've got A, B, C, and D, so that's what we're going to load into it. On our output cues, I've got A, B, C, D, just like it has in the textbook. I've given you a list of hints down the side here. These are the actual answers that we're looking for. So the first thing we're going to do is do a clear. So when we press the clear line low or put a 0 on the clear line, all our outputs are going to be 0. We're then going to load the number 1000 on the preload lines. And S0 and S1 are both going to be 1. So it should load 1000 into our shift register. Now DSR, so our data from shift right, we're not going to touch. Because when you look at our schematic, when we get over to QD, it's going to feed back into the data for shift right. So we don't need to put anything on that line. So the data line for shift left is going to be 0. And what we're going to do is put S0 at 1 and S1 at 0. And we should start shifting right. So we started with 1 in the leftmost column. It should move over one position, and then it should move over another position, and then it should move over another position. And because we've got that QD hooked up to SR, it should now recirculate back into the first position and then shift across with each clock pulse. So once we've shifted our 1 bit to the rightmost position the second time, we're then going to put S0 and S1 at 0 and 0. This is the hold mode. So for the next several clock pulses, it should just stay at 0, 0, 0, 1. Then we're going to put S0 at 0 and S1 at 1, and it should start shifting left. So on the hint here, it was in the rightmost position. Now it should shift left one position, and then another position, and then another position. And then because we have the data for shift left at 0, the next clock pulse it should shift in a 0 for us. So I just wanted to give you a close-up of my completed circuit. You can see I have my dip switch in, my SIP resistor, the +5 going to the first pin of my SIP resistor. The blue line is my clock signal coming in. The yellow lines are my outputs to the Qs or the LEDs. The green lines are from my switches to control my IC. So right now I have all the switches in the up position. So I'm going to turn on my trainer. So the first thing they want us to do on the truth table is to move the clear switch to logic 0. So my first switch is my clear switch. I'm moving it to logic 0. So all my outputs are 0. In the next line of the truth table, we want to do a parallel load. So A is going to be 1, B is 0, C is 0, and D is 0. My DSL line is supposed to be 0. And right now, this is my S0, and you can see it's at 1. And this is my S1, and you can see it's at 1, and my reset line is still resetting. So I want S0 at 1, I want S1 at 1, and I want the clear line to be at 1. So you can see on the next clock pulse, it did do the parallel load. So I am sitting at 1, 0, 0, 0. Now I want it to shift right. For it to shift right, S0 has to be 1 and S1 has to be 0. So this is my S1. It needs to be 0. And then it recirculates and comes back again. Now to put it in hold mode, both S1 and S0 have to be at 0. So I'm going to let it circle through one last time. And now I have it in hold mode. Now we want it to put it into shift left mode. So to do that, S0 is 0 and S1 is 1. So S0 is 0 and S1 is 1. And now you can see it shifting to the left, and then the final 0 shifts in. So I've now filled in my truth table. When I cleared it, it was all zeros. When I did the parallel load, I had 1, 0, 0, 0. When I shifted it to the right, every clock pulse, it moved over one position, and then it recirculated in and continued to move over one position. I did hold it when it got to the last or rightmost position, and then I had it shift left. So then it started on each clock pulse to shift left, and then on the final shift, all zeros were on my outputs. Once you've wired up your third circuit and verified that it is working, demonstrate it to your instructor so they can initial it to indicate that it is complete. On the last page, we have 10 questions for you to answer and hand in. If you are looking for answers, open your textbook. Page 1 of this lab shows some hints, and here we can see we're looking for solve problems 11.1 to 11.28.